In this video, we're going to take a look at linear rates of change. The rate of change of a linear equation is a measure of how quickly the dependent variable changes with respect to the independent variable. We measure this rate of change a lot of times through something called a slope. So that is what we're really going to take a look at today. How do we measure this slope? Slope is denoted m and can be found by taking the change in y over the change in x, or to write that out a little bit more formulaically, m is equal to change in y over change in x, or y2 minus y1, being how much the y's have changed by, over x2 minus x1. To see how this works, we're going to jump right into some examples. First, let's find the slope of a line passing through the points 4, 1, and 6, 3. So now how points work, this 4, 1, that must give us an x and a y coordinate. And in the 6 and 3, that gives us a different x and y coordinate. Now, which one we call x1 and x2 really doesn't matter. You might be saying, well, isn't the 4, 1 the first point and the 6, 3? I mean, sure, yes, in a sense, but if we're looking at a line is continuous in both directions. There's no first and second point, so it really doesn't matter. I'm going to choose to call this 4 and 1 the x1, y1. That means the 6 is our x2, and then 3 is our y2. So if I set up my equation for slope, y2 was the 3, minus the y1, which is 1, over x2, which is 6, minus x1, which is 4. So again, the y2, 3, minus the y1 of 1, x2 of 6, y1 of 4. And that's how I got my numbers. When I subtract 3 and 1, I get 2. 6 minus 4 is 2, and 2 over 2 is equal to 1. So that would be our slope. Now I might be saying, well, what if we switched it? You told me it didn't matter. What if we switched this to x2, y2, x1, y1? So let me do this calculation again, but using the numbers in an opposite order. So this time I'm going to start with my y2 of 1. I'm going to subtract my y1 of 3. On the bottom, I'm going to start with the x2 of 4, subtract the x2 of 6. 4 minus 6. So on the top, I am getting a different number. It's a negative 2. On the bottom, I'm getting a different number. It's a negative 2 as well. But guess what? What is negative 2 over negative 2? Because both the numbers ended up at the opposite sign, we end up at the same positive 1. Our slope is equal to 1. Doesn't matter how we do it. We only need to do it one way, but it doesn't matter which way we do it. So the key is to be consistent. It does not matter what you call x1 and x2, but you've got to be consistent. Obviously, the x has got to be in the first position, but the second I chose that 4 to be the x1, the 1 has to be the y1. The second I chose the 4 to be the x2, the 1's got to be the y2. We've got to be consistent. Let's take a look at another example. Let's find the slope of a line passing through negative 2, 4, and 6, negative 1. I'm just going to do this one once, so I'm going to call this first point x1, y1, and this next one x2, y2. Don't need to write down which ones are which, you just need to keep it in your head, but I don't think it hurts to write it down either. So our slope will be equal to, the y2 is a negative 1, the y1 is the 4, so negative 1 minus 4. The x2 is 6, I subtract, the x1 was negative 2. So here I'm subtracting a negative. Remember, a double negative always turns into a positive. So because I always have to subtract negative 1 minus 4, that's subtraction. That gives me negative 5. But then in the bottom, we have 6 minus the negative 2. That gives me a positive 8. So we end up with a slope of negative 5/8. There's nothing to simplify on that one. So calculating the slope is pretty straightforward. Let's take a couple examples how we can apply this. How will we use this? The temperature within a car increases linearly from 60 degrees at 1 p.m. to 85 degrees by 5 p.m. How quickly is the temperature changing per hour? So we want a rate of change. It's a linear rate of change. So what that tells us is we're looking at the slope. Now I don't have points x1 and y1, x2 and y2, but we can think about these as some relationship of independent and dependent variables. We want the temperature per hour, meaning temperature over hour. That means the temperatures are going to be on the top, so they're going to be equivalent to our y's. So I'm going to call this 60 the y1, and 85 the y2. Per hour, temperature per hour, that means that the time should be in the denominator. So 1 p.m., that was my first time, I'm going to call it x1. And the 5 p.m., that must be the x2. I could also write these as the points, 160, 585. Remember, a function is just anything that takes one number to another number. It takes an independent variable to that dependent variable. And so we're taking times to temperatures, and that's going to give us the temperature per hour. Now I'm going to set up my equation. 85 minus the 60 over 5 minus 1. 85 minus 60 is going to be 25. 5 minus 1 is 4. And so it might be easier to, we could write this as an improper fraction, but because we're discussing time, or because we're discussing temperature per time, it might be easier to go ahead and reduce this. And so I could write this as 6 1/4 or 6.25. I've got to think about my units. And remember, it was temperature per hour. So this would be saying 6.25 degrees per hour. So if I want to answer this in a complete sentence to really explain what's going on, what this tells me, the temperature in the car is increasing at a rate of 6.25 degrees per hour. And there would be my answer. Take a look at this next example. Car manufacturer makes $250,000 more for every 50 additional cars that they sell. How much do they make for every additional car? So how much money for every car? We want to know money over cars. So that means the money must be the y's, the cars must be the x's. So here this 250, that must be talking about the y, the x is 50. Well, this seems like a problem. We only have 2 points. 1 point. We only have one x and one y, 2 numbers. But if we think about how these are phrased, car manufacturer makes 250 more, and then 50 additional. That's actually already giving me an amount of change. How much more are the y's? The y's are 250,000 more. How many more are the x's? They are 50 more. So they're giving me those rates of change within the word problem. I don't have to calculate a y2 minus y1 because the problem has given it to me. So I'm just going to take these two numbers and divide them. And when I divide 250,000 by 50, I get 5,000. And because we're talking about monies per car, or dollars per car, this would be 5,000 for every car. So to answer my question, how much more do they make for each additional car? The car manufacturer makes an additional $5,000 for every car. Every car they sell, they're going to make $5,000 more in profit. Let's look at one final example. So now we've seen an example where we had to take the x and y and 2 different points, use that official formula, and then we've had this last example where we were given those rates of change. That's kind of like this first one here, just the change in y is given to us, the change in x was given to us. And then last here, as the forest next to a new housing development is cleared for new houses, deer are leaving the forest. If there were 150 deer initially and only 40 deer 3 years later, at what rate are the deer leaving the forest? What rate are they leaving per year? So we see deer per year. So we're going to be using the deer as the y's and the time or the years as the x's. So I see one initial starting amount of deer, that's my y1. And I see a amount of deer, second amount of deer, that's 40, that's my y2. And this 3 years later, that is associated with the x, but 3 years later, like with the last example, that's not saying a point of something and of 3, that's saying 3 years have passed. That is the change in x. So I can think of this as that change in idea. So we're kind of mixing those two formulas. On one hand, I'm going to have to calculate the y2 minus y1 on the top. I have 40 deer now, or y2 is 40. 150 was the initial. And how much time has passed? 3 years. So we're going to take our 40 minus our 150 first. That'll give us negative 110. Then we're going to divide that by 3. and we get negative 36.6666 or negative 36 and 2/3. Now, might be looking at that saying, well, wait a minute, is a negative right? And yes, because things can go up or they can go down. Here the deer are leaving, so it makes sense that it would be negative. The number should be negative because that's indicating that we have less than before. The last two examples, as the x was going up, as the independent variable was going up, so too was the y. As the temperature of the car increased, so too, as the time progressed, so too did the temperature increase. And then in the last example, as we make more cars, we make more money. But in this case, as time progresses, we actually have fewer and fewer deer. So we can say every year, 36 and 2/3 deer leave the forest. Forest with one R. Well, 2/3, does that really make sense? Remember, this is kind of an average idea where, yeah, we're not going to actually have 2/3 of the deer leaving the forest, but if we were to look the day before, maybe it'd be 36 deer, the day after it'd be 37 deer. So it's just kind of that midpoint for something that's not going to be, day-to-day specific. On average, we see 36 and 2/3 deer leave the forest. So that is how we are going to go about calculating our slopes, our rates of change, our linear rates of change. It is this idea of a change in y over change in x. We have a formula to use if we have points given. We can also just think about it in terms of the ideas of what does it mean to be changing.